welcome back. So, we have been looking at the resolution refutation method, and we first looked at it for propositional logic, and we saw that the procedure is as follows, that you take the given knowledge base, you negate the goal and add it to the knowledge base, convert this whole thing into CNF or clause form, and then repeatedly apply the resolution rule by taking some two clauses and adding the resolvent, and you keep doing that till you empty the empty clause as a resolvent. And then we said, okay, let us look at this method in first order logic, and we saw how to express the formula in a form which is suitable for application of the resolution method, and the form that is suitable is called the clause form, in which we have eliminated the quantifiers and we have arranged the rest of the formula into CNF like structure, conjunctive normal form like structure, and taken care to standardize variables apart in every conjunct essentially. Now, we are interested in finding proofs. So, as with propositional logic, the procedure for finding a proof is similar. Convert each premise into clause form, negate the goal and convert it into clause form. So, now it is a conjunction of clauses. Add the negated goal to the set of clauses. Choose two clauses such that the opposite sign literals in them can be unified. So, if some atomic formula and one clause has an atomic formula, the other clause has a negation of the atomic formula, then you can remove that from both. Resolve the two clauses using the most general unifier, and we have seen what is the procedure for constructing the most general unifier, and add the resolvent to the set essentially. Repeat steps 4 and 5 till the null resolvent is produced. Very similar to what we did in propositional logic, except that we have to handle all these variables and quantifiers here. What is the resolution rule for first order logic? For the sake of completeness, we assume that each clause can have multiple instances of the same literal with maybe different variables or different constants thrown into the picture. So, for example, in these two clauses C1 and C2, C1 has a set of clauses which are L1 or L2 or Lk, and what we are trying to say here is that they look similar essentially, in the sense that L1 may be use the same predicate name and L2 will use the same predicate name as L1, their variables may be different and things like that. So, if we can find a most general unifier for all the Li's and all the Ri's, then you can see that Li's are positive atomic formulas, Ri's are negative literals, and we can cancel all of them together, and what we would be left would be all the P formulas and all the Q formulas, and we would construct a new formula which has all the P's and all the Q's, but making sure that the substitution theta that we use for constructing the MGU is applied to this formula essentially. This is for the sake of generality. When we do solve small problems, especially in quizzes and exams, we do not have this complex things, except once or twice you might suddenly find a clause which has 2 instances or 3 instances of the same formula. Maybe in the quizzes we can look at those. So, we begin with our oldest pattern of reasoning, the Socratic argument, which said that if we have the clause all men are mortal, which we earlier said was for all x man x implies mortal x, but now into clause form it is expressed as not man x or mortal x. Clause 2 is man Socrates, and the negated goal that we have added is not of what we wanted. What we want is that mortal Socrates. This is the goal, and we negate it and add it to the this thing. After that, it is just a small process here. From C1 and C2, we can generate mortal Socrates by saying that x is replaced by Socrates. That is what we wanted, but because of the fact that we are using the resolution refutation method, our goal now is to derive the empty clause, and that is straightforward here because we have the negation of the goal. We have already derived the goal in R1, and so R2 becomes the empty clause. When we started with first order logic, we said that we have the rule of universal instantiation, and you can see that this substitution is in a way like doing instantiation. We are replacing the formula by replacing the variable in the formula with a constant in this case. So, we can see the proof here as a DAG or acyclic graph, directed acyclic graph, and you can see that in the shaded portion is what captures the forward chaining. In the forward chaining, from man Socrates and all men are mortal, we inferred mortal Socrates, and so in some sense this resolution rule subsumes forward chaining. Whatever you can do with forward chaining, you can also do with resolution method or resolution rule. Of course, for the sake of completeness, we have added the negation of the goal, which is shown in orange here, and derive the null clause. That is the goal in resolution refutation method, is to derive the null clause. You can see that you can see this same resolution DAG as doing backward chaining. So, if you think of this orange formula, the negated formula, as a goal, and we had seen this parallel that when you say that something is a goal, you could add the negation and you could think of it as a goal. So, if you are thinking of it as a goal, then supposing we use the phrase show, mortal Socrates. Then in backward chaining, we replace it by saying show man Socrates. That was backward chaining, and exactly the same step is happening here, that from not mortal Socrates, which is the negated goal, we get a new negated goal, if you want to call it, not man Socrates, and that can be satisfied trivially because it is there in the knowledge base, and so we can say there are no more goals to be solved. So, if you remember the backward chaining procedure, that is being subsumed by resolution rule. So, the resolution method is in some sense a generalization of both. Whatever backward chaining can do and whatever forward chaining can do, the resolution method can also do. So, here is the Alice problem. So, notation that I have used is a little bit mixed. Remember that we had this Charniak and McDermott list notation in which there were no mathematical symbols. So, I have used that notation, but I have used mathematical symbols also here, because sometimes I find it easier to read those formulas here essentially. So, otherwise I would have written this as not all likes x m likes x a. This would have been the in purely in the list notation, but I use a mixture of those two things, that instead of using this prefix connectives, I have used the infix one, which is more readable, at least for me, I think. So, this is the Alice problem converted into clause form. and this last one is the negated goal clause, as we have been seeing essentially. So, this is what we have. The clauses all drawn neatly on this slide, and the negated goal clause essentially. And we can go through the steps one by one. So, first we cancel this likes Alice stories with not likes Alice stories, and what we get is likes Alice physics, which is the resolution rule. Then using that and using the rule that if she likes algebra and if she likes physics, then she will go to college, we have reduced it to a new rule which says if she likes algebra, then she will go to college, because the fact that she likes Alice stories has already been taken care of. Then somewhere independently we say that that she, if she likes maths, then she likes algebra, and then we said that she likes maths, and then from that we infer that she likes algebra, which is like doing modus ponens, but now we are doing the resolution rule essentially. So, from that, the fact that she likes algebra, and from the clause which said that either she likes algebra or she goes to college. So, we inferred that she goes to college. That is what we wanted to show, but since we are doing the resolution refutation method, we go one more step and show that we can derive the null clause from the negated. So, in this, some of the examples that we have seen, which are tiny examples, the conclusion is actually proved, for example, here, and then the process is completed by negating it with the goal, but it is not always the case. And if that was the case, then forward chaining would be same as resolution method, or backward chaining would be same as resolution method, but that is not the case. There is some situations where the negated goal plays an earlier role essentially. In fact, when people work with the resolution refutation method, people say that you must try to use the negated goal as early as possible, because of the fact that if there is a contradiction in the augmented knowledge base, what is the augmented knowledge base? The knowledge base augmented with the negation of the goal, and if there is a contradiction in the augmented knowledge base, it must be because of the negated goal, essentially, because ultimately we are doing proof by contradiction. So, some people say that you must try to use either the negated goal or its descendants as early as possible. So, this strategy is called set of support strategy. Set of support strategy says that try to use the negated goal as early as possible. Here we have used it in the very end. So, as a small exercise, I will ask you to start by using the negated goal in the first resolution step, and then try to use either that or what was derived from that, and you will see that that also works well essentially. The other strategy we talked of was unit strategy. I did not write this in slides, but I hope this will suffice for you to remember. Unit strategy says that use a unit clause like this one as far as possible. Why? Because unit clauses will reduce the other clause by length 1. So, you can see that here we have a clause of length 2, it got reduced to a clause of length 1, and when we use this unit clause, then this clause of length 3 got reduced to a clause of length 2, and then that got reduced to a clause of length 1, and then that got reduced to a clause of length 0. So, unit clauses obviously have this tendency of shrinking the other clause, because they cancel off that negated literal. And so, that is one good strategy. The other is that because you want to derive the contradiction, you use the set of support strategy, which says that use either the negated goal or its descendants in that. We will come back to this variation of set of support strategy later. Let us address this problem that has been bugging us ever since we introduced it in first order logic. We said that you are given this knowledge base O of A B, O of B C, M is not A is not M, and C is M, and from that we had this goal that there exists an x and a y. Remember that these are existentially quantified variables such that x is not m and y is m and O whatever between x and y. O is looking at x is looking at y or x is on y depending on your interpretation. So, that was what we could not do then. So, let us now see how this happens in the resolution method. So, we started with the premises, 4 premises that we had, and we negate the goal and add that as a additional clause to that. Now, you will see that we will start using this negated goal pretty soon. In fact, the very first thing that we derive is from 4 and 5. What is 4? 4 is m c, and what is 5? It says that there is something which is not m. So, y is not m. So, if we say y equal to c, then we can eliminate that, but we must substitute y for c. So, this c has come because it was y to start with essentially, and now we have a new formula. Similarly, from 3 and 5, what is 3? 3 says a is not m. Now, if we say in formula number 5, if we say that x must be a, that substitute x with a, then if we do that, we can cancel that not m a with this one here. This gets cancelled with this. So, we are left with the other two disjuncts in the clause, and this y has carried forward here essentially. Now, from 1 and 7, we can cancel O A B, because here it says not O of A with something, and if that something happens to be B, then we can cancel that, and what we will be left is the other part, which is not m that thing, and that thing is b, because we have said y is equal to b. So, we get not m b essentially. In a similar fashion, we get m b from 2 and 6. 2 says O B C, and 6 says this formula, which is not of O something something, not of O something C. We can cancel that not of O something C, which is here, with O B C, which is here, and we would be left with the remaining part, which is m of b, because x has become b. And now, of course, we have the empty clause. So, you see that something that we could not do in first order logic, in forward chaining or in backward chaining, we can do in the resolution method. So, not only does the resolution rule subsume forward chaining and backward chaining, it can do more than that essentially, and this is what we have seen here. And we have also seen that in this example, the negated goal played a role in deriving the null clause. It was used quite early in the proof essentially. So, the two other simpler examples that we saw, in which it came in the very end, like the police in some of our Bollywood films, this is not always the case. For problems which are more complex, it has to play an early role. And you can see, if you think about this, you can see that this will come to a large extent because of the occurrence of the or in the this thing in some formulas essentially. So, the disjunct is not so straightforward to deal with essentially. The same proof, if you read it in the Bloch's world domain, you can now read it as on A B, on B C, not maroon A, not maroon C. Show that there is an x and y such that x is maroon and y is not maroon and x is on y. That is a negated goal, sorry. And then the same proof, it is just that I have renamed the predicate names with what we used in the earlier proof. The same thing would apply here, except that in this proof the names are what I used to use earlier. So, Jack and Anne and John, instead of Cuthbert and Archie that I had used, but that does not matter. I mean, what is in the name. So, you can again show that the empty clause can be derived essentially. So, this shows, this illustrates the fact that resolution method is complete, it could solve problems that forward chaining and backward chaining could not solve essentially. We will take a break and we will come back and talk about equality. When we started with talking about first order logic, we said that there is a special symbol, special predicate called equality, and if we use that, then it is called first order logic with equality. So, in the next video or in the next class, we will see how to handle equality, as to what else do we need if we are using this predicate. So, see you